The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
I'm going to show you a bunch of different things. A lot of this isn't new. It's stuff I've taken from various projects, and some practical projects, some research projects. But just to bring John's point, I threw in a couple of slides on synergistic effects of Portland limestone cements with slag and ternary blends at the end, just 2 slides, just to keep you to the end. And a couple of these slides actually overlap with Mike's talk because some of them were joint projects. But I stuck with silica. The reason I stuck with silica, fume, and slag mainly for this talk is because that's what we do in Ontario. We have all this, the steel industry in Canada is all in Ontario. And so slag is right close to the biggest population density in Canada, so it gets used. And silica fume comes across the border from Niagara Falls or down the stream from Montreal area. So we have those are 2 main materials. We tore down our last coal plant over a year ago, so we don't have any coal production anymore. So we have to import flash from the US now if we want to use it. And they still do it. So I'm going to talk about those 3 things if you take the PCA slide: slag, Portland, and silica fume. And again, this is maybe old hat at this point in the series here. There's a bunch of good things that supplementary cementing materials do. And you create more calcium silicate hydrate, uses up more calcium hydroxide, it fills more space. The timing of this is important because you set an initial pore system from the Portland cement. With the exception of silica fume, these things happen later. So you subdivide the pore structure in a secondary hydration. And Jan mentioned as well the interfacial transition zone of the aggregates becomes a lot denser. So you pick up the strength of the coarse aggregate, and silica fume has been great for doing that to help us utilize high-strength concrete because you're basically utilizing the coarse aggregate strength. And certainly in Toronto, you can change the mix design. You don't have to change the mix design. You just have to change the coarse aggregate if you want stronger concrete. You bring in a stronger aggregate, you can get another 20 MPa out of the concrete just by changing the coarse aggregate because you're developing that strength of the bond. But there's other fun stuff too. Because of this lower calcium to silica ratio of the hydrates, these hydrates that do form with supplementary materials allow more substitution of things into that calcium silicate hydrate. We get more alkali substitution. It binds alkali, which is one of the issues related to the ASR mitigation. You're reducing the pore solution alkalinity, but it also binds up alumina. So the sodium and potassium are making up for the calcium deficiency, but the alumina also comes in there and substitutes in there, and the alumina substitution increases binding by chlorides and by alkalis. So it does a whole bunch of good things, and people don't always realize the small things. However, with things like flash and slag, often that initial rate of reaction is slower, especially at higher replacement levels and especially in cold weather. But you can redesign mixes. I mean, the ready-mix industry is pretty sophisticated. They can redesign mixes to give you a property at a given age, no matter what's in the concrete. Because you've got chemical admixtures and other things you can play with in the mix design. So certainly in Toronto, we change replacement levels with season because we go from very hot weather in the summer to really cold weather in the winter, especially this winter. It's terrible. So they have to adjust, to make adjustments. If you want to deliver concrete that performs the same in the winter and in the summer, you have to make adjustments to the mix designs in that sort of environment. Now, since slag came into the market in Ontario in 1976, and it was so successful in the marketplace that every cement producer started grinding slag separately, and every ready-mix plant in southern Ontario has been using slag pretty much. But right after the fact, silica fume came on the market, although it wasn't widely used till about the mid-'80s. And then around the mid-'80s as well, they started playing with these blended silica fume cements that Mike mentioned. Cement companies found that they could handle it a lot easier because the ready-mix plants sometimes had trouble handling separate silica fume at the time, so they interground the silica fume with the Portland cement and made those products available. So anytime pretty much that they use silica fume in Ontario, they also put slag in the mix. And I'll try and explain some of that stuff. So typically we use in any concrete, any ready-mix producer, 25% slag replacement. And that number comes from the highway department because they just decided that 25% they could accept that without any special provisions. And if you want to use higher numbers for heat of hydration or sulfate resistance, which they also do allow, you can do that. But 25% for general medi-mix is in all the concrete. For higher numbers, like I said, ASR or chlorides or sulfates, they use higher numbers of slag replacement. But again, we deal with weather effects in that thinking. The silica fume cements they've been making, some of them have varied, but typically they're around 8% plus or minus 0.5% or so when they set their targets. And every one of the cement producers in Ontario makes a blended silica fume cement. And again, the reason they do this is it makes it easier to handle at the ready-mix plant, as long as they've got a silo for that extra material. And if they have a blended silica fume cement, if they want to lower the amount of silica fume, they can mix it with straight Portland at the ready-mix plant, so you can make a 4% silica fume mix or whatever you want, and then, of course, you add the slag. Some of the concerns with silica fume initially were finishing problems. The first speaker talked about stickiness, the word, but that was the problem the finishers had. They had to learn how to finish it. There were plastic shrinkage concerns because the same old sort of bad, sloppy practices that people did with normal concrete weren't sufficient when you got to silica fume concrete with something that doesn't bleed, and you get, as soon as you don't have any bleed water, it's prone to that plastic shrinkage cracking. And so ternary cements have a lot of advantages. You can reduce the high-range water reducer doses significantly with slag relative to a straight silica fume mix. The contractors had an easier time placing it. The finishers seemed to like it better. It didn't stick to their tools as much, and some of the automatic paving machines had less problems with it. Fewer contractor complaints, always a good thing. And it gave good early age resistance properties as well as the later age properties. So Mike talked about this earlier. You get the early age from the silica fume property improvement. You get the later age from the slag improvement. And of course, heat was another issue. When they started using this in high strength concrete in Toronto, some of these columns would get up to 80 or 90 degrees Celsius in these 2-meter diameter columns in high rise. You could almost cook your lunch on it. So putting the slag in reduced that temperature and reduced the risk of thermal cracking. And of course, reducing the high-range water reducer is a good thing because admixtures usually add to the cost. It's like your dinner. You usually pay more for the liquids than the solids when you're consuming your dinner. Well, at least maybe in Canada. Maybe you don't do it here. So anyway, we get this improvement at early age from the silica fume. It has less effect at later ages. Mike showed that quite nicely with his long-term data. Slag gives you better resistance at later ages. It doesn't kick in immediately, but by 7 or 14 days, it's starting to equal Portland cement. And by 28 days, it's doing much better, and it gets better for a long time continuously. So the ternary blend gives you the synergistic effect that all the speakers have talked about of doing things at early age and later age to get the best of both worlds. And here's just some data that goes way back, work we did on permeability a long time ago, just showing at early ages. Just water permeability on a log scale versus early age, starting at 1 day measurements. You just take a straight mortar. These were mortars, 0.45. Slag and Portland cement are pretty similar at 1 day, but you can see that slag's lagging behind there. I've only gone out to a week here. But silica fume, you're starting off at more than an order of magnitude lower permeability from the get-go at 1 day. So you're getting that initial kick and lower permeability even at 1 day from the silica fume, and you can see it's following along, not a dissimilar curve, but it's following along at at least an order of magnitude lower value of that. Just to talk about this age thing, this is, difference between slag and Portland cement. This is just 3 mixtures, 0, 25, and 50% slag. We did this at a constant water content and a constant water cement ratio, because you've got 2 variables if you want to change permeability. You've got the water cement ratio, which affects the porosity of the paste, but the water content is your initial porosity of the concrete, so your water content also impacts, and that's what you can control with aggregate optimization and use of chemical admixtures. So we kept all those constant, and you can see the slag, this is at 90 days. The strengths are not too dissimilar, 5 megapascals. It's not that much. But you see a big reduction in the rapid chloride permeability. The coulombs go down by a factor of 5, and the water permeability almost goes down by the same exact number. So again, this is old, really old data. We've done somewhat more recent data. It's only 12 years old, where we looked at early age permeability again with concretes, with slag. And if you look at it, start measuring at 3 days here, 2 or 3 days, you can see the slag is an order of magnitude worse for an equivalent concrete. These were 35% slag, 0.40 water cement ratio, or water cementitious ratio. And you can see the slag is an order of magnitude worse at 1 or 2 days, but by 4 or 5 days it's equivalent, and by a month and a half, it's an order of magnitude better than the Portland cement. So it's changing because it needs that extra time, but it continues to improve. We didn't do it any further than that 49 days, but it just shows the crossover. We did do work on conductivity, and a lot of people talk about resistivity. Conductivity is just the inverse of resistivity. And essentially, with a rapid chloride test, you are measuring conductivity, but multiplying it by time to get coulombs. So if you just measure the initial conductivity, bulk conductivity of different mixes, and these are concretes with different mixtures, this high-performance mix has 6% silica fume, 25 slag, and what you see here, it's that green line. And it comes down, has the lowest conductivity, which means the highest resistivity, which means it's the least permeable to ionic species. And it's coming down. This is 28 days, 7 days, you see that. Whereas the straight Portland cement is the blue line. The silica fume on its own is this guy here, just slightly above the ternary mix. So the ternary mix is better than the straight silica fume, even at relatively early ages. And Mike's talked about this reduction with time of diffusion coefficient. If you plot on a log-log scale, you typically get a linear fit of reduction of diffusion, or any transport property pretty much, with the log of age. And this is what's used in Life 365 to modify the coefficient, because you measure your coefficients at something like 28 days, but 28 days number isn't good enough. You need to know what's going to go on with time, because it has a huge impact on things like service life prediction. And this is one of Mike's slides, which I didn't get off my webmail. I just stole it from you, showing, again, schematically. These aren't real numbers. It's schematic. If you had a Portland cement, and Mike showed real data, which is more important, that if you start at 28 days and started with a value, yeah, the Portland cement gets better with time, but not a lot better. The slag typically is in the same order at start, but it gets a lot better with age. Silica fume starts, like I say, almost an order of magnitude lower, but it doesn't get a lot better with age. But if you use the combination of those, the sort of purplish line, you get the best of both worlds. You get the reduction at early age, and you get this long-term reduction with time because of the slag. And of course, you're interested in the 10,000 days, or that's somewhere about 30 years, 30 to 50 years in that range. And there's just a bit of data. This is Coulomb data with age. Again, this is a straight Portland cement. We're seeing reduction in coulombs from 28 days out to about a year here. And you see the reduction. This is a silica fume mix. It's fairly flat. You get the big reduction at early age, but it's not going anywhere. With the slag and silica fume, maybe not quite as steep, but we're seeing reductions with age. You get the benefit at early age plus an improvement with time. And I'm just going to blow by that one. Just to show the difference, though, we did some work way back on water permeability. And we were trying to measure different water cement ratios, and this is apples and apples. But if you take a straight Portland cement concrete, and this is a high water cement ratio, we got a value of permeability. You drop it from 0.69 to 0.49 water cement ratio, it drops by about an order of magnitude. So we think, well, we'll go down to 0.29, what happens? But we added silica, we used a ternary vex here. Instead of dropping another order of magnitude, it dropped 3 orders of magnitude on the water permeability. This is right at the extreme limits of measurement in those concretes. And Mike mentioned the binding capacity. These are some binding slides from a student that Mike and I supervised years ago, showing that if you have a straight Portland cement, you get a certain amount of binding. This is bound chlorides versus the chloride solution samples in. And if you add fly ash or slag, you get increasing amounts of binding. There's metakaolin up here. And you're basically doing this in the order of increasing alumina in the system, the binder system. The more alumina, the more binding you get of the system. Silica fume has less binding than straight Portland cement because it's pure silica. There's no alumina. So you're actually getting reduced chloride binding in that case. So a ternary mix, you use the slag or fly ash. You can compensate for that and get increased binding. So I'll move on and talk about some of the high strength for a minute, just a few slides. The first time we used silica fume in high strength in Toronto was 86. And it was first, well, I've said 10 here. It's probably 20 towers now that have used these ternary blends of silica fume and slag. Typically using in the range of 7 or 8 silica fume, or actually less now because they're diluting it out, but 25% slag. Initially they were specifying 70 MPa. This is the core, the elevator cores and the columns, and they were getting 85, 90 megapascals. The big thing they wanted here, because they were jump forming and they wanted to raise these towers at 1 floor every 3 days, they needed 20 MPa at 11 hours. So 3,000 PSI at 11 hours, and they were getting it, but it was being pumped. They did one pump operation from bottom to top. There was no room on site, so there was an old abandoned gas station across the street. They set up a pump station, ran the pipes underneath the street, and just pumped about 100 meters horizontal and up to 300 meters vertical. And they were able to do that, and they used liquid nitrogen cooling because they were doing this in all weather. And even in the summer, they could take this thing down to about 10 degrees C in the concrete because they had a maximum 18 degrees C in the forms requirement for that concrete because they didn't want to lose the high-range water reducer and lose their slump in the process. And temperature is really critical to that. So as long as they met, and they were able to meet the 18 degree in the forms with that concrete. That's another one of the towers here. That's the Bay BCE towers. There's a pair of those towers. Again, that used 85 MPa. This is another tower, the Shangri-La. You can see the boom up there under construction. And again, using 85 MPa. It's pretty standard in Toronto. There's about 4 ready-mix companies that can deliver that concrete if you just call them up. This is a listing of 5 towers that went up with the original 70 MPa specified. The strength requirement wasn't a 28-day strength requirement. It was a 91-day strength requirement. And they were getting typically 85 up to 95 megapascals at 91 days. The standard deviations on the first 2 were a bit higher because this is before they had the pre-blended silica fume cements. They decided after these 2 jobs that they put 2 requirements in: no more truck mix concretes. The first 2 were truck mix concretes, so batch plants. They had to have a pre-mix plant, and they had to use the silica fume blended cement. So those were the 2 changes, and you can see that the coefficient of variation on strengths went down when they made those changes. And then later on, so that's 70 MPa. That was the limit of what they could get with the coarse aggregate, the local limestones. So for 85 MPa, they brought limestone in from Manitoulin Island by boat to the shore in 30,000-ton loads because they have water access, and this is stronger, denser limestone. They didn't make any changes to the mix design except they changed the coarse aggregate. So now you're getting 85 MPa specified, and they're getting strengths in the order of 100 megapascals or more in that, and no difference in the coefficient of variation. So just by changing the coarse aggregate, because they developed the strength of the coarse aggregate because of that good interfacial transition zone that allowed them to do that. I'll talk a bit about precast. Precasters typically use highly strength cement because they don't want to wait. They want to get things out quickly, especially for AASHTO girders. They want to release the strands. They want strengths and probably even faster. They typically want something faster than 18 hours. Well, so we did some work on this a long time ago to show that they could do that, and we're using 65 degrees C. And so we're trying to show them they could use these mixes in precast plants, even though they typically don't think they could. So we set up a steam profile. We followed the requirements of the precasting standard, the still Canadian one, with terms of temperature rise rates, holding the temperature, and coming down again. And so then we measured the strengths at 18 hours. Type of mix, we're using 0.3 water cement ratio, total cementing materials at 460, air entrained, 6 to 8 inch slump. And these are the strengths we were getting at 18 hours. There's the straight Portland cement. There's increasing silica fume. They wanted 40 MPa at that time frame. We were able to get 45. Then we used a ternary mix with silica fume and slag. We were also able to get 40 megapascals. And the long-term strength was better with the ternary mix, the 28-day strengths. But they were able to get the release strength with the ternary blends. In terms of Coulomb values, see the same thing. Here's the values just with 7 days moist curing at room temperature. There's the heat treatment. You see the difference. And one thing you see in heat treatment, typically with heat treatment, if you heat treat Portland cement, the permeabilities go up. You change the nature of the pore structure that's formed at the high temperature, and you typically get higher values. Even with a small amount of silica fume, we still saw that same effect. But when you get enough silica fume or the ternary mixes, it actually reduced at the high temperature curing. So you didn't see the negative effect on chloride penetration with the blended cements in the high temperature curing. And again, we did bulk diffusion values. Again, this was back then that Mike talked about the fact there was no test, and they were using this other test method at the time with a 120-day diffusion test. So at that time, that's the test we were using. And we did tests for the 23-degree cure ones, like room temperature cured, and the accelerated curing regime. And you can see, again, the cement showed higher diffusion rates. When we got enough silica fume in, that differential disappeared. And with the blended cements, we were getting low numbers, even with the steam curing. And again, that's just a graphical form of the same thing, showing that the ambient curing is the black lines, the steam curing are the gray lines, and if they moist cured post-steam curing, they got the white lines. It really didn't make much improvement. In fact, I've just done a study on high-performance concrete for the industry that finished last year, and with, again, ternary blends, we're not seeing, after the steam curing with these ternary blends, we're not seeing the benefit of post-moist curing of those things, which is a big issue because the way the standard is that the precasters don't have facility to post-moist cure in many cases. The influence of that was very small. So the steam curing with these high-performance mixes is working quite well for them. Well, and this, Mike's already shown this, so I won't bother. There's the mix design for the Shepherd subway that he mentioned, which was the first use of the ternary with slag in precast tunnel liners. That was the length of tunnel finished at the time. But you can see there's the numbers here. Slag, we've got this blended silica fume cement, about 300 kilograms, 150 kilograms of slag, 0.31 water cement ratio. They were getting more than their design strength. They were able to meet their diffusion coefficients and their water permeability values. And you're looking at about 38% cement replacement in these mixes. And there's some data from the work. Mike was a co-author in that paper showing the various diffusion data and the Coulomb data of these mixtures, these ternary mixtures, showing that they're getting these very low numbers. In terms of bridge ducts, slipping back to cast-in-place concrete, some of the first high-performance bridge ducts were done at the airport in Toronto. They were, like every airport in the world, they're always under construction. They redid a new terminal, and all the arrivals and departures decks are ternary blend silica fume slag concretes, and the 40 bridge structures on site are as well. And they poured the first one in 1999 with slag and silica fume at 0.40. And they did even continuous pours in very cold weather up to 1,200 cubic meters. And they had no problems whatsoever from the get-go. And all the properties were good. I'll show you some data in a second. And they just finished an inspection 2 years ago on all those bridge structures, and there have been no problems from a durability point of view on those bridge structures at the airport. But that's typical values. They were getting about 7-inch slump, well air and trained with a good spacing factor. You're getting about 50 MPa with good standard deviations. The Coulomb's about 600. And the bulk diffusion values were low. So we measured bulk diffusion on cores taken from those, and they're getting low values. That was on the first bridge deck. We also did some parking decks with silica fume slag mixtures in Toronto, and again, this goes back to 1998. And we did it in the worst possible weather. It was about 95 Fahrenheit with the wind blowing and the sun out, so it was just perfect for plastic shrinkage cracking on these big decks. So they had a fairly large deck. They used silica fume cement with 30% slag, 0.37. It was a 6,500 PSI air and train job. They pumped it all. They had 3 pump systems, 3 finishing crews, and they're getting under 200 coulombs at 2 months, and again, a low diffusion coefficient. This was the key to success on that job. Was fog misters. This is before you could buy them at your local building supply place. For power car washers, we actually took burner nozzles and modified them onto a portable power washer. And with this hot day, again, you're just misting across that forest, that huge space. As long as you're on the upwind side, we had to tell the guy which corner to stand on. There were no plastic. There was one plastic shrinkage crack about 6 inch long. The next when we went out and looked after the fact on this deck. So in spite of the pretty severe conditions with high winds and the sun, because they used the fog misting on this, they were able to avoid plastic shrinkage cracking. Now, Mike's mentioned the ASR, so maybe that's so I can cut the time. The big thing is the pore solution alkalinity reduction. This is pore solution alkalinity in terms of hydroxyline concentration or some of the alkalis, and you have increasing slag replacements of Portland cement. We want to be below about this red line, about 300 millimoles per liter, or 0.3 molar. This is straight slag there, so you need about 40% slag to get below that threshold. If you add 5% silica fume, you can do that with about 20% slag. If you use 8% silica fume, you can do it with about less than 10% slag. So you can use the ternary combination to play with the mix designs to get what you need to get, to reduce the alkalinity such that there won't be enough alkalinity to attack the aggregates anymore. That was at 90 days. Same data at 2 years. So you've got pore solution alkalinity at 2 years. Again, you see the same trends. As you add slag, you get the reduced alkalinity. More with silica fume and slag, you reduce it more. That dotted line up there is what would happen if you just diluted the cement. You assumed you put sand in there or something. So it's doing more than that in terms of reducing the alkalinity. Okay. I'm not going to go there. Mike's already shown that, so I'm not going to show it. That was the other study that he already showed. One thing, I'll just mention 2 slides on this. We did another study at Kingston. In fact, we wrote this paper 2 years ago if you want to read more about it, again with 6 concretes. I think this was the first ASR exposure site in Canada. And there's Mike actually praying that the concrete won't crack. So we did a bunch of beams reinforced in plain beams and some slabs with these different mixtures. And there's one ternary mixture in there 25 slag and about 4% silica fume. It would have been higher, but we ran out of silica fume. We had to bag it into the truck. So that's what we ended up with. But it turns out after 20 years, it worked really well. So here's expansion of the big blocks. They're 2-meter-long blocks, and we measured the expansion of these over 20 years. And you can see that the high-alkali cement cracked up pretty early on after about 3 years. Even the low-alkali cement cracked up after 6 years. 25 slag or 18% ash weren't sufficient with this this is sprat, again, fairly reactive aggregate. 50% slag worked, but also the 25 slag with the almost 4% silica fume, after 20 years, they're just not expanding. So we've got good performance from those things. You can read that paper if you want from ACI Materials Journal. And I just throw in the last 2 slides, if I may. This is, I said about limestone. We take a straight cement. GUL is limestone cement with 9% limestone in it. GUL 15 is 15% limestone. You can see here the strength development at different ages, that the limestone cement works well with the slag. We're actually getting better strengths at 7 days than we did with the straight Portland mix with those same slag replacement levels. Here's the limestone cement with silica fume and slag, so a Ternary cement, and we're getting excellent strengths at all ages with half the clinker replaced in those mixes. And just to put it in terms of coulombs from a durability perspective, there's the coulomb values at 1 month, 2 months, and 6 months. Again, we're getting low numbers with the Ternary blends, and we're getting lower permeabilities with the 40 and 50 slag with Portland limestone cement than we are with the straight Portland cement on its own. So the Portland limestone cement plus slag works better than the straight Portland cement with slag. So we're getting that benefit of the carboluminate phases forming. So I just wanted to throw that in at the end. So you get the synergistic effect. We're getting good performance at early ages and later ages using these ternary blends, and we get enhanced durability. So better ASR performance, better sulfate. I didn't talk about sulfate resistance, but we do as well, and better resistance to chloride ingress, and we're getting good strength at all ages.